Look up at the night sky. What do you see? A scattering of bright dots, familiar constellations, maybe even the faint glow of the Milky Way. But here's the mind-bending truth. What you're seeing is just a fraction, a tiny whisper of the universe's grand story. For every star visible to the naked eye, there are countless others hiding in the shadows, so distant, so strange, or so secretive that they slip past even our most powerful telescopes. These aren't just ordinary stars, they're cosmic ghosts flickering in the void. They're light trapped by time, space, or forces we're only beginning to understand. Imagine a star so massive it warps space itself into a one-way trapdoor, swallowing its own light before it can reach us. Picture another, born in the early universe, already dead by the time its faint glow begins the journey toward Earth, a celestial echo of something long gone. These aren't science fiction, they're real, they're out there, and they defy everything we think we know about the cosmos. Some are cloaked in dust clouds thicker than any fog, while others race away from us so fast their light stretches into oblivion, red shifted into silence. And then there are the ones that simply shouldn't exist, stars so bizarre they rewrite the rules of physics with every pulse of their dying light. This is the story of the universe's best-kept secrets. 30 hidden stars you'll never see but that shape the cosmos in ways we're only starting to unravel. They're the ghosts in the galactic attic, the whispers at the edge of detection, and together they paint a picture of a universe far stranger, far wilder than the one we thought we knew. So let's journey beyond the visible, beyond the known, and uncover the mysteries of these elusive cosmic wonders, because sometimes what we can't see tells us the most about who we really are beneath this vast starry sky. Some stars don't burn, they devour the invisible. Before the first flicker of nuclear fusion lit up the cosmos, there might have been another kind of star, one fueled by something far stranger, dark matter. These wouldn't glow in the familiar blaze of hydrogen and helium. Instead, they'd feast on particles we still struggle to detect, particles that outweigh ordinary matter 5 to 1 in the universe. Imagine a celestial body so dense, so cold, it wouldn't shine in any wavelength we know, a black orb hanging in the void, radiating nothing but the faintest heat as dark matter annihilates at its core. These are dark stars, and if they exist, they'd rewrite the first chapter of cosmic history. Unlike modern stars where gravity's crush ignites nuclear fires, a dark star would grow massive beyond imagination, stretching up to 10 million times wider than our sun, without ever sparking the fusion we associate with starlight. Instead, a hypothetical WIMP, weakly interacting massive particles, would collide and obliterate each other in its heart, releasing just enough energy to keep the star puffed up like a dying ember. No dazzling surface, no solar flares, just an eerie gravitational whisper in the dark. Why haven't we found one? The answer lies in time. Dark stars could only form in the early universe when dark matter was densely packed, and even if they linger today, their signatures would be nearly impossible to spot. Telescopes hunt for light, but dark stars offer none, no flicker in the infrared, no shadow against distant galaxies. They're cosmic phantoms, detectable only by their gravitational fingerprints on surrounding matter. Yet if they're real, their remnants could be hiding in plain sight, masquerading as supermassive black holes at the centers of galaxies. The irony is poetic. The universe's first stars might have been its most alien, invisible architects shaping everything that came after. They challenge our definitions, asking not just how stars live, but what it even means to be a star when the rules are written in particles we've never seen. But what if a dying star doesn't stop collapsing at a neutron star? What if the pressure becomes so unimaginably intense that even neutrons, those impossibly dense building blocks of matter, shatter into something even stranger? Enter the quark star, a cosmic anomaly so extreme it defies the very laws of physics as we know them. When a massive star explodes as a supernova, its core can collapse into a neutron star, where protons and electrons fuse into neutrons packed so tightly a sugar cube-sized chunk would weigh as much as a mountain. But under even greater pressure, the neutrons themselves might break apart into their fundamental components, quarks. These aren't the neatly arranged quarks inside protons and neutrons. They're a chaotic, seething ocean of strange quark matter, a state so dense and alien it could be the true ultimate form of matter in the universe. The physics here bends reality. A quark star would be smaller and denser than a neutron star, perhaps only 12 miles across, yet weighing twice as much as the Sun. Its surface wouldn't be solid or even gaseous, but a swirling plasma of quarks, held together by forces so strong they create a near-perfect frictionless fluid. And here's the eerie part: quark stars might be self-bound, meaning they don't rely on gravity to hold themselves together. The quarks themselves, through sheer fundamental force, could keep the star from collapsing further. Why haven't we found one? Detection is a nightmare. Quark stars would look almost identical to neutron stars, same size, same dim glow, same rapid spin. The only telltale signs would be subtle differences in how they cool over time or emit gravitational waves. Some astronomers suspect a few known neutron stars, like the mysteriously massive object at the heart of supernova remnant 328, might actually be quark stars in disguise. Others theorize that quark stars could form when two neutron stars collide, their combined gravity triggering a phase transition that unshackles quarks from their neutron prisons. The implications are staggering. If quark stars exist, they'd prove that quark matter is the universe's most stable state, more stable than atoms, more stable than neutrons. That would mean chunks of this strange matter could drift through space, and if one touched Earth, it might convert ordinary matter into quark matter in a chain reaction. Don't worry, there's no evidence this has happened, and the odds are astronomically low. But the sheer possibility shows how quark stars aren't just celestial oddities. They're windows into a reality where the rules we take for granted no longer apply. They challenge us to rethink the boundaries of matter itself, proving that even in death, stars can become something far stranger than we ever dreamed. Some stars don't just die, they get swallowed alive. Picture a cosmic Russian nesting doll where a dying red giant wraps itself around the dense corpse of a neutron star, creating a celestial hybrid so bizarre it sounds like science fiction. This is the Thorne-Zytkow object, a theoretical monster that blurs the line between star and stellar graveyard. The story begins with a close-knit stellar duo. When a massive star in a binary system explodes as a supernova, its core collapses into a neutron star, a city-sized remnant so dense it defies comprehension. But if the explosion doesn't kick the neutron star away, it might spiral into its bloated companion, burrowing deep into the red giant's core. There, shielded by layers of hydrogen, the neutron star becomes a ticking time bomb, slowly siphoning material from its host while stirring up a nuclear maelstrom. What makes this object so strange isn't just its structure, it's the chemistry. Normally, red giants fuse hydrogen into helium in their outer shells, but with a neutron star at the heart, convection dredges up unusual elements like rubidium, lithium, and molybdenum, creating a stellar fingerprint unlike anything else in the universe. These elements should be destroyed in typical stars, yet here they accumulate, painting a spectral signature that screams, something unnatural lurks inside. So why haven't we spotted one? The challenge lies in the camouflage. From the outside, a Thorne-Zytkow object would look like a slightly peculiar red giant, its exotic heart hidden beneath layers of gas. Astronomers have candidates like HV 2117 in the Small Magellanic Cloud, which shows odd chemical abundances, but confirmation requires catching the star in the act of exhaling its neutron core's influence. Some models suggest these objects might eventually reveal themselves through violent outbursts, as the neutron star's gravity shreds its host from within, triggering eruptions visible across galaxies. The irony is profound. The universe might be hiding these chimeras in plain sight, their existence whispered only in subtle chemical quirks. They force us to question what makes a star normal, and whether the cosmos has more surprises lurking behind the familiar glow of aging giants. If found, they wouldn't just be curiosities, they'd be living proof that stars can cheat death by becoming something entirely new. Deep in the cosmic voids, where galaxies thin to mere specks and the darkness stretches for millions of light years, there might lurk stars so cold they defy everything we know about starlight. Imagine a celestial body not blazing with heat, not shimmering with fusion, but hovering just a whisper above absolute zero, the coldest possible temperature in the universe. These are frozen stars, theoretical anomalies so chilly they emit almost no visible light, their surfaces colder than the frost on Pluto's poles. How could a star, an object we associate with searing heat and blinding radiance, become so frigid? The answer lies in their birth. While most stars ignite from collapsing clouds of gas, frozen stars could form in the deepest, emptiest regions of space, where stray atoms drift so far apart they rarely collide. In these near-perfect vacuums, a loose clump of hydrogen might slowly gather over billions of years, never reaching the density needed to spark nuclear fusion. Without that internal furnace, the star would never turn on. Instead, it would languish as a dark, icy sphere, glowing feebly with only the residual heat left over from its formation, a fossil from the early universe preserved in cosmic deep freeze. Spotting these ghosts is a nightmare for astronomers. Infrared telescopes designed to detect heat signatures would struggle because frozen stars radiate at wavelengths too long and faint for current technology to distinguish from background noise. Even their gravity would be nearly undetectable, too weak to noticeably warp light from distant galaxies behind them. The only hint of their existence might come from rare, ancient clouds of gas that move strangely, as if tugged by an unseen, frosty hand. Yet if their real, frozen stars could rewrite the rules of stellar evolution, they'd prove that not all stars must blaze, that some might exist in a state of near-permanent twilight, silently drifting through the voids between galaxies. More than cosmic curiosities, they'd be reminders of how much we still don't understand, how the universe reserves its darkest corners for the strangest secrets, where even the concept of a star can freeze solid into something entirely new. The universe is young, too young for some stars to finish dying. Among the most patient corpses in the cosmos are black dwarfs, the final, frozen remains of white dwarfs that have cooled to absolute zero over trillions of years. Right now, they're purely theoretical because not enough time has passed for even the oldest white dwarfs to fade into this state of perfect darkness. A white dwarf is what's left when a sun-like star exhausts its nuclear fuel, shedding its outer layers to leave behind a smoldering core no larger than Earth. For billions of years, it glows faintly with residual heat like a dying ember in a cosmic campfire. But given enough time, far more than the current age of the universe, that ember would cool entirely, radiating away its last whispers of warmth until it becomes a cold, inert lump of crystallized carbon and oxygen, a black dwarf. Think of it as a stellar fossil, a shadow of what once was. Black dwarfs wouldn't just be dark, they'd be virtually undetectable. No light, no heat, no magnetic fields, just the faintest gravitational tugs betraying their presence. Even if one lurked in our cosmic backyard, our telescopes would struggle to spot it against the void. The only way to confirm their existence would be to witness their subtle influence on passing stars or dust clouds, bending starlight like a ghostly lens. What makes black dwarfs so eerie isn't just their invisibility, but their inevitability. Every white dwarf in the universe today is destined to become one given enough time. They're the ultimate fate of most stars, including our own sun, a silent, frozen in-game written into the laws of thermodynamics. By the time the first black dwarfs form, the universe will be so old that all other stars will have long since burned out, leaving these dark relics as the last remnants of a vanished era of light. The irony is haunting. The universe hasn't existed long enough to produce the very objects that will outlast everything else. Black dwarfs are a prophecy of cosmic heat death, a reminder that even stars can't shine forever. They challenge our sense of time, forcing us to confront the unimaginable stretches of eternity where even the slowest processes must finally reach their end. Black holes terrify us with their infinite hunger, regions of space where gravity wins so completely that not even light escapes. But what if there's something even stranger lurking in the darkness? Meet the gravastar, a theoretical cosmic oddity that flips the script on everything we know about gravitational collapse. Picture a black hole's opposite. Instead of a singularity, it contains a bubble of dark energy, a force so repulsive it could halt the crushing weight of a dying star in its tracks. At first glance, a gravastar would look almost identical to a black hole, same intense gravity, same light-bending effects, same ominous silhouette against the cosmos. But peel back the layers and the differences become staggering. While a black hole's core is infinitely dense, a gravastar's heart would be a swirling void of dark energy, pushing outward with such ferocity that it prevents total collapse. Surrounding this exotic core, a shell of ultra-dense matter, thin as an atom yet tougher than diamond, holding the entire structure together like a cosmic eggshell. The implications rewrite physics. Gravastars wouldn't have event horizons, those one-way boundaries that make black holes inescapable. Light could theoretically skim their surfaces and escape, though it would be stretched and warped beyond recognition. More bizarrely, because dark energy accelerates the universe's expansion, a gravastar might actually grow slightly over time, its core exerting outward pressure against the pull of gravity. So why haven't we found one? The challenge is in the details. Gravastars would mimic black holes so precisely that even our most advanced instruments, gravitational wave detectors, X-ray telescopes, might struggle to tell them apart. The key difference lies in subtle echoes. When black holes merge, their gravitational waves ripple outward in a clean, dying pattern. A gravastar collision, however, might produce faint after ripples, vibrations from that dark energy core resonating through space-time like a struck gong. Not all physicists are convinced. Critics argue that gravastars require matter to behave in ways we've never observed, violating quantum laws or stability thresholds. Others counter that in a universe dominated by dark energy, such structures might be inevitable, just waiting for us to spot the right cosmic fingerprint. Whether real or not, gravastars force us to confront the limits of our knowledge. They remind us that black holes might not be the only monsters in the dark, and that the universe's most extreme phenomena could still be hiding in plain sight, disguised as something we only think we understand. At the very edge of theoretical physics, where the familiar rules of stars twist into something unrecognizable, there might exist a celestial freak of nature, the electroweak star. Unlike any star we've ever observed, this one wouldn't rely on nuclear fusion to shine. Instead, its power would come from forces so fundamental they govern the universe just fractions of a second after the Big Bang. Picture a star squeezed beyond the point of mere atomic collapse. As matter compresses to densities trillions of times greater than a neutron star, protons and electrons cease to exist as separate particles. They melt into a seething plasma where the electromagnetic force and the weak nuclear force, two of nature's four fundamental interactions, merge into a single primordial fury. This is the electroweak phase transition, a state so extreme it hasn't occurred naturally since the universe was a trillionth of a second old. In the heart of an electroweak star, these forces reignite, converting quarks into pure energy at rates dwarfing even the most violent supernova. The energy output defies belief. For a fleeting moment, perhaps just 10 million years, an electroweak star could outshine entire galaxies, its core burning at temperatures surpassing 10 quadrillion degrees. That's not just hot, it's a heat so intense it recreates conditions last seen when the cosmos was raw, unformed energy, yet this brilliance comes at a cost. Unlike stable stars that burn for billions of years, an electroweak star would consume itself like a match struck in a hurricane, its fuel exhausted in a cosmic blink. So why haven't we spotted one? The answer lies in their rarity and the razor-thin window for their formation. An electroweak star could only arise if a collapsing supernova core avoided becoming a black hole by the slimmest margin, halting its collapse at the precise density needed to trigger electroweak burning. Even then, detecting one would be a nightmare. Their light would be drowned out by the very forces powering them, their signatures blurred into the background noise of the universe. Some theorists suggest their death throes might leave behind exotic remnants, black holes wrapped in swirling layers of electroweak plasma, or faint echoes in gravitational wave data. Yet the sheer audacity of the idea challenges our understanding. Electroweak stars shouldn't exist under known physics, but neither should dark energy or quantum entanglement until we proved they did. They force us to ask what other impossible monsters might be lurking in the equations we've yet to test. The universe has a habit of outrunning our imagination, and sometimes the strangest stars aren't the ones we see, but the ones we dare to dream. Black holes might not be the endless voids we imagine. They could be cosmic time capsules hiding a secret from the universe's first moments. Deep within their crushing depths, beyond the point where space and time break down, there might lurk a Planck star, a fiery remnant of quantum gravity, smaller than an atom yet hotter than the Big Bang itself. This isn't science fiction. It's a radical twist on Einstein's equations, where the infinite collapse of a black hole's core is halted by the universe's smallest possible scale, the Planck length. Picture a star collapsing under its own gravity, squeezing past the neutron star phase, past quark matter, until it reaches a density so extreme that space-time itself rebels. According to loop quantum gravity, one of the leading theories attempting to unite relativity and quantum mechanics, gravity could flip from an attractive force to a repulsive one at this scale. Instead of vanishing into a singularity, the star's core would rebound like a spring compressed to its limit, exploding outward in a burst of energy. But here's the catch. This explosion happens behind the black hole's event horizon, invisible to outside observers. The Planck star would be trapped, its light and energy circling endlessly in the prison of its own gravity. The numbers defy comprehension. A Planck star's diameter would be roughly 10 to the power of -35 meters, a billionth of a trillionth the size of a proton. Yet its temperature would approach 10 to the power of 32 Kelvin, replicating conditions last seen a split second after the Big Bang. This isn't just a star, it's a fossil of creation itself, a pocket of primordial fire preserved in the darkest corners of the cosmos. How could such a tiny object exist inside a black hole? The answer lies in quantum foam, the turbulent fabric of spacetime at microscopic scales. Just as water can't be compressed beyond a certain point, spacetime might resist infinite collapse, forming a dense, frothy structure where the Planck star flickers like an ember in a cosmic storm. Some theories even suggest these stars could eventually evaporate as the black hole around them decays via Hawking radiation, their energy leaking out over millennia like steam from a sealed kettle. The implications rewrite cosmic history. If Planck stars exist, dying black holes might not vanish silently. They could end with a pop, releasing stored energy in a final, faint echo of their birth. Astronomers search for these echoes in the cosmic microwave background, subtle ripples that could betray the presence of long-dead black holes. Others speculate that colliding black holes might briefly expose their Planck cores during mergers, releasing bursts of high-energy particles detectable by future observatories. Yet the greatest challenge is the veil of the event horizon. By definition, nothing inside can communicate with the outside universe, leaving blank stars forever hidden from direct observation. They exist as mathematical ghosts, their reality debated in equations and thought experiments. But if proven real, they'd bridge the gap between quantum mechanics and gravity, solving the paradox of the singularity while offering a glimpse into the universe's most violent birth pangs. They remind us that even in the darkest pits of space, the universe might still be playing by rules we've yet to fully understand, rules written not in fire or light, but in the whisper-thin boundaries of the quantum world. Every star you see might have a secret dance partner, hidden in the darkness, clinging to the gravitational embrace of a bright, familiar sun, are cosmic phantom stars that refuse to shine. These aren't just dim or distant, they're celestial ninjas invisible to every telescope, their existence betrayed only by the wobbles and tugs they inflict on their radiant companions. Take brown dwarfs, for example, too massive to be planets, yet too small to ignite the fusion fires of true stars. These failed stars smolder in infrared obscurity, weighing down their visible partners with silent gravitational insistence. Some are colder than a winter night on Mars, emitting less heat than a candle flame across light years. Others lurk so close to their host stars that their presence is only revealed by subtle rhythmic dimming, like a shadow passing behind a curtain. Then there are the rogue planets, orphaned worlds flung from their birth systems, now bound in reluctant orbits around unsuspecting stars. These drifters don't reflect or emit enough light to be seen directly, but their gravity leaves fingerprints. A star might twitch inexplicably, its path through space tracing tiny, precise circles as if tugged by an unseen hand. Astronomers call this astrometric wobble, and it's often the only clue that something massive and utterly dark shares the star's celestial neighborhood. The hunt for these invisible companions is a cosmic game of hide and seek played with math and patience. When a star's light blue shifts and red shifts rhythmically, it's not just moving toward us and away, it's likely locked in an orbital tango with an unseen partner. The speed and pattern of these shifts reveal the hidden object's mass and distance, even if it emits zero light. Some of these dark companions are shockingly close, like the suspected brown dwarf orbiting Epsilon in Dye just 12 light-years away, its presence deduced from the star's erratic path. But the real mind-benders are the ones that shouldn't exist at all. Stars like KIC 8462852, where something massive, maybe a black hole, maybe a cluster of rogue planets, passes in front of it at irregular intervals, blotting out up to 20% of its light. No known object fits the data neatly, leaving astronomers to wonder, what kind of invisible behemoth could warp starlight so dramatically without leaving a trace? The galaxy might be teeming with these ghostly partners, rewriting the rules of stellar relationships. They force us to admit how much of the cosmos is hidden in plain sight, detectable only by the ripples they leave in the fabric of space. After all, the universe loves its mysteries, and sometimes the most profound secrets aren't written in light, but in gravity's silent whisper. Before the first stars flickered to life, before galaxies spiraled into shape, the newborn universe might have birthed stars of an entirely different kind, not from gas and dust, but from the gravitational clutches of black holes older than time itself. These wouldn't be stars as we know them, blazing with nuclear fire. Instead, imagine celestial monsters forged in the chaos of the Big Bang, their cores not of fused atoms but of primordial black holes, relics from the universe's first terrifying moments. Primordial black holes aren't like the ones formed from dying stars. They could be as small as a single atom or as massive as 1,000 suns, born when dense regions of the early cosmos collapsed under their own weight. Some theorists suggest these ancient black holes might have clustered together, their gravity pulling them into tight knots that could mimic the appearance of stars from afar. A primordial black hole star wouldn't shine. It would be a swirling hive of these invisible predators, their collective mass bending light like a lens, their presence betrayed only by the way they warp the space around them. Their connection to dark matter is where things get eerie. If these black holes exist in vast numbers, they could account for the universe's missing mass, the invisible glue holding galaxies together. Unlike other dark matter candidates, they wouldn't require exotic particles, just gravity, pure and simple. A single primordial black hole drifting through a modern star could devour it from the inside out, leaving behind a cold, dark husk. Others might lurk in the voids between galaxies, their faint gravitational ripples the only sign of their existence. Why haven't we found them? Detection is a nightmare. A solitary primordial black hole the mass of a mountain would be smaller than a proton, emitting no light, no radiation. Just the faintest whisper of Hawking radiation if they haven't already evaporated. Even if one passed through our solar system, its gravitational tug would be so subtle we might mistake it for a rogue planet or a glitch in our math. The best hope lies in microlensing, where a black hole's gravity briefly magnifies the light of a distant star, creating a telltale flash. But these events are rare, fleeting, and easily drowned out by cosmic noise. The most unsettling possibility, some primordial black holes could be lurking in our own backyard. If they're small enough, they might zip through Earth like bullets through fog, leaving behind microscopic tunnels of superheated rock, traces so faint we'd need a quantum microscope to spot them. Others might orbit invisibly in the outer solar system, their gravity nudging distant objects like Sedna onto strange, looping paths. Whether they're the missing piece of dark matter or just cosmic ghosts from a forgotten era, primordial black hole stars challenge our understanding of what a star even is. They remind us that the universe's first light might have been preceded by something far darker, an age where the night wasn't just empty but crowded with silent, hungry shadows. Some stars don't just shine, they strangle their own light with invisible fists of magnetism. Imagine a celestial body so magnetically ferocious that its field twists space itself, bending photons into knots before they can escape. These aren't your average magnetars, though those are terrifying enough. We're talking about magnetic monsters so extreme they warp the very rules of visibility, rendering themselves nearly undetectable in the cosmic glare. Take a magnetar's already absurd strength, 1 trillion times Earth's magnetic field, and crank it up another order of magnitude. At these intensities, something bizarre happens. Quantum electrodynamics, the bedrock theory of light and matter, starts to fray. The vacuum of space around the star becomes polarized, a hall of mirrors where photons split and merge in ways Einstein never predicted. Light trying to flee the star's surface doesn't just redshift, it spirals into chaotic loops, trapped in magnetic whirlpools thicker than planetary orbits. To distant astronomers, the star would flicker like a dying bulb before vanishing entirely, its light smothered in its own magnetic prison. Why haven't we spotted one? The universe has cruel irony baked into its design. The same forces that make these objects so extreme also erase their fingerprints. X-ray telescopes hunting for magnetar bursts, those violent magnetic hiccups, would find nothing. Radio observatories tuned to pulsar beacons would hear silence. Even gravitational wave detectors might miss them, as their oscillations could be muffled by the very fields distorting spacetime around them. The only hints might come from secondary effects, ghostly distortions in background starlight, or rogue gamma-ray flashes when a magnetic snare briefly snaps, releasing pent-up energy like a cosmic spring uncoiling. The connection to known magnetars is tantalizing. Ordinary magnetars already defy logic, their fields are strong enough to rip atoms into spaghetti-shaped strands. But what if some were born with even stronger fields? Simulations suggest that in the chaotic collapse of a massive star's core, magnetic flux could become hyper-concentrated, like winding a rubber band until it's poised to snap. The result, a star that doesn't just crack under magnetic pressure but folds inward, its own light crushed beneath layers of invisible force. What's truly unsettling is the longevity. While most magnetars fade as their fields decay over millennia, these theoretical ultra-magnetized beasts could persist far longer, their energy locked in magnetic structures that resist dissipation. They might lurk in plain sight, disguised as black holes or cold neutron stars, their true nature hidden behind curtains of warped spacetime. The universe loves its paradoxes, objects so magnetically vibrant they become darkness itself. They challenge our definitions of what it means to be seen and remind us that sometimes the most powerful forces in the cosmos are the ones that leave the faintest traces. What if the universe has an invisible twin, a hidden cosmos where stars and galaxies exist, yet remain forever beyond our sight? Enter the ghost stars, celestial specters forged not from ordinary atoms, but from mirror matter, a theoretical substance that shuns all but the faintest interactions with the world we know. These aren't just dim or distant, they're built from an entirely different kind of particle, moving through space like phantoms in a parallel dimension. The theory hinges on symmetry, one of physics' most elegant principles. Just as left and right hands mirror each other, mirror matter proposes an entire shadow universe where particles spin the opposite way, governed by the same forces but with flipped properties. A ghost star made of this stuff wouldn't emit, absorb, or reflect light as we understand it. Its protons, electrons, and neutrons, if it even has them, would be mirror versions, oblivious to the electromagnetic force that paints our cosmos in color. To our telescopes, these stars would be voids, their presence revealed only by the gravitational ripples they leave in ordinary matter. How could such a star form? Picture the early universe, a seething soup of particles and antiparticles annihilating in bursts of energy. If mirror matter exists, it might have avoided this fate, clumping into clouds that collapsed under their own gravity without ever igniting the nuclear fires we associate with starlight. These dark cinders could have seeded entire mirror galaxies, vast, silent structures interwoven with our own, their gravity sculpting the visible cosmos from behind the curtain. The dark matter connection is irresistible. If ghost stars and their mirror galaxies outweigh ordinary matter 5-1, they'd perfectly explain why galaxies rotate faster than their visible mass suggests. Unlike other dark matter candidates, WIMP, actions, or sterile neutrinos, mirror matter doesn't require new physics, just a doubling of particles we already know. Yet proving their existence is a nightmare. Collisions between mirror and ordinary matter would be vanishingly rare, like two sheets of sandpaper grazing each other in the dark. The only hints might come from ultra-sensitive experiments hunting for anomalous particle recoils or the faint heat signatures of mirror photons leaking through dimensional cracks. The most haunting possibility, ghost stars could be right beside us. A mirror matter asteroid might have punched through Earth unnoticed, its impact registering only as a seismic blip. A mirror black hole could orbit invisibly at the edge of our solar system, nudging comets onto odd trajectories. Even our own sun might have a ghostly twin, a mirror star bound to it gravitationally, circling in perfect, undetectable synchrony. They force us to confront a chilling thought. The universe we see might be the barest sketch of what's actually there, with whole chapters written in ink we can't perceive. If ghost stars exist, they're the ultimate cosmic hide-and-seek champions, revealing just enough to haunt our equations, but never enough to step into the light. Near a black hole's crushing embrace, time doesn't just slow, it fractures. Imagine a star caught in this gravitational tempest, orbiting so close that the laws of relativity twist its very existence into a cosmic freeze frame. To us watching from a safe distance, that star's light dims, stretches, then stops, not because it's gone, but because time itself has stretched into an infinite whisper. This is the fate of a time-dilated star, a celestial prisoner locked in a moment it can never escape. Einstein's theory of relativity paints the nightmare scenario. As gravity intensifies near a black hole, time dilates, meaning clocks tick slower the deeper they sink into the gravitational well. For a star skirting the event horizon, this effect becomes extreme. From our perspective, each second on that star's surface could stretch into years, centuries, even millennia. Its light, struggling to climb out of the black hole's gravity well, gets redshifted into oblivion, wavelengths stretched so thin they fade into undetectability. The star's final moments, whether it's being torn apart by tidal forces or slowly cooling, would appear to us as a single, frozen instant, lingering at the edge of visibility like a cosmic still life. The math behind this is both beautiful and brutal. Light emitted from the star's surface near the event horizon would take exponentially longer to reach us with each subsequent photon. The star's last gasp, its final burst of light before crossing the point of no return, might never arrive at all, trapped in an endless relay between gravity's pull and the fabric of spacetime. To distant observers, the star doesn't vanish. It becomes a ghost, eternally suspended in its own death throes. Astronomers call this gravitational time freezing, and it's not just theoretical. We've observed hints of it around supermassive black holes like Sagittarius at our galaxy's center. Stars like S2, which orbits perilously close, show measurable time dilation in their light, a subtle redshift that betrays the warping of spacetime around them. But for stars even nearer to the edge, the effect would be so severe that their entire life cycles would appear to halt from our vantage point. A supernova that should take seconds could look like a century-long slow-motion explosion. The cruel irony, from the star's own perspective, nothing unusual happens. Time passes normally on its surface until the moment of destruction. It's only our distant view that's distorted, as if peering through a funhouse mirror where physics itself becomes the illusionist. This disconnect between observer and participant is relativity's greatest magic trick, proof that the universe has no universal clock, only a web of perspectives tangled in gravity's grip. What's even stranger is that some of these time-frozen stars might not be alone. Binary systems where one star has already collapsed into a black hole could have their surviving partner locked in this relativistic limbo. We might never see it vanish, only fade into an ever-dimming twilight, its light stretched into radio silence. These stars challenge our most basic assumptions about time and existence. They're cosmic monuments to relativity's power, reminding us that even the simplest things, a star's light, a moment's passing, are never as straightforward as they seem. In the face of such extremes, the universe doesn't just hide its secrets, it bends them, stretches them, and sometimes freezes them in place forever. Picture a star stretched into a needle-thin line, warping space around it like a crack in the fabric of reality. This isn't a glitch in the simulation. It's what might happen if a star gets tangled in a cosmic string, one of the most bizarre relics predicted by theoretical physics. These strings aren't made of anything we'd recognize, no atoms, no particles, just pure spacetime defects left over from the Big Bang, thinner than a proton but denser than a neutron star, vibrating with the energy of 1,000 suns. A star snagged by such a string wouldn't just orbit or collide, it would be reshaped. The string's unimaginable tension, millions of trillions of times stronger than steel, could slice through a star like a wire through cheese, pulling it into a filament millions of miles long. The result, a celestial noodle glowing faintly as it dangles from the cosmic web, its gravity bent into strange, intersecting ripples. From afar, it might look like a star split into multiple copies, lensed by the string's space-time warping grip, a cosmic funhouse mirror where one star becomes a shimmering chain of mirages. Detecting these string-bound stars is a physicist's nightmare. Cosmic strings themselves are invisible, leaving no light to catch, no heat to measure. Their only signatures are the gravitational tremors they'd send through space-time ripples so subtle they'd drown in the noise of merging black holes and neutron stars. Even if a star were caught in one, its distorted light might blend into the background of ordinary stellar oddities. The best hope lies in spotting the impossible. A star whose light bends in ways no black hole or dark matter clump could explain, or a galaxy mysteriously sliced into identical halves by an unseen scalpel. The wildest possibility, these strings might still be out there, weaving through the cosmos like spider silk. If they exist, they'd be fossils from the universe's first trillionth of a second, when spacetime itself was cooling from a roiling quantum foam. Some theories suggest they could form loops, vibrating at frequencies that shred passing stars into glowing debris, transient flares blinking in the darkness without explanation. Others think they might connect distant parts of the universe like hidden shortcuts, their gravitational wakes leaving trails of orphan stars drifting in perfect, eerie alignment. What makes cosmic string stars so unsettling isn't just their strangeness, it's the quiet revolution they'd represent. Finding one would prove that spacetime isn't smooth and featureless, but scarred with ancient defects, a crumpled canvas from the moment of creation. They're reminders that the universe's most profound secrets might not lie in the glow of stars or the spin of galaxies, but in the invisible stitches holding reality itself together. Most stars announce their presence with blinding light or crushing gravity. But what if a star existed that could slip through your hand like smoke? Enter the neutrino star, a celestial phantom built not from atoms, but from the universe's most elusive particles. Neutrinos barely interact with matter, passing through entire planets as if they weren't there. Yet under conditions so extreme they defy physics as we know it, these ghostly particles could theoretically clump together, bound not by electromagnetism or nuclear forces, but by gravity's faintest whisper alone. The birth of a neutrino star would require a cataclysm beyond any supernova. Picture a hypernova explosion so violent that it shreds the very protons and neutrons of a dying star's core, reducing them to a soup of quarks and leptons. In this primordial fury, neutrinos, normally fleeting byproducts of nuclear reactions, could become trapped, their sheer numbers overwhelming their tendency to escape. If enough congregated in one place, their collective gravity might forge a fragile bond, creating a shimmering, diffuse sphere with the mass of a sun but the density of morning mist. You could fly a spaceship straight through one and never know. A neutrino star wouldn't block light or cast shadows. Its particles are so indifferent to matter that photons would sail through unimpeded. Even its gravity would be deceptive. Without a dense core to warp spacetime sharply, its pull would feel more like a gentle tide than a black hole's grip. The only hint of its presence might come from rare neutrino interactions, where a stray particle collides with an atom in a detector, sparking a blip drowned in cosmic noise. Current technology stands no chance of finding one. Our most sensitive neutrino observatories, like IceCube buried in Antarctic ice, are built to catch high-energy neutrinos from distant cataclysms, not map the faint thermal murmurs of a hypothetical neutrino star. Even if one lurked in our galactic backyard, its signal would blend into the background chatter of solar and atmospheric neutrinos. Some theorists suggest looking for distortions in the cosmic neutrino background, the faint afterglow of the Big Bang, where a neutrino star's gravity might warp the paths of these ancient particles like a lens. The wildest implication, neutrino stars might not stay invisible forever. If dark matter consists of sterile neutrinos, hypothetical, heavier cousins to the ones we know, they could collapse into similar structures, their extra mass making them slightly more detectable. Others speculate that in the far future, as the universe cools, even ordinary neutrinos might gain enough relative mass to clump together, seeding invisible stellar corpses that outlast all conventional matter. These ghostly orbs force us to rethink what makes a star real. They exist in the equations before the data, in the gaps between what we see and what must be. After all, if the universe can build stars from pure light or twisted spacetime, why not from particles so shy they barely acknowledge reality exists? Galaxies aren't supposed to move like this. Across the cosmos, vast clusters drift not just with the universe's expansion, but in a peculiar, synchronized flow, as if tugged by something beyond the edges of our observable reality. Astronomers call this enigma the dark flow, and its source remains one of cosmology's deepest mysteries. But hidden within this cosmic current might lie stars unlike any other. Dark flow stars, celestial bodies hurled into the void by forces so vast, so distant, they defy the very limits of our telescopes. These aren't ordinary runaway stars ejected by supernova or galactic collisions. Dark flow stars move with purpose, their trajectories aligned with the mysterious pull affecting entire galaxy clusters. Their velocities break the rules too fast to be explained by visible matter's gravity, too coordinated to be random. Imagine a star streaking through space at thousands of kilometers per second, not fleeing from anything but racing toward something, an unseen attractor lurking in the unreachable darkness past the cosmic horizon. The implications rewrite our cosmic map. If dark flow stars exist, they're cosmic breadcrumbs, hinting at structures so colossal they warp the fabric of the universe on scales we can't comprehend. Perhaps a supermassive cluster of galaxies trillions of times heavier than the Milky Way looms just beyond our observable bubble, its gravity bending space-time like a hidden magnet. Or maybe it's something stranger, a flaw in the early universe's inflation, a primordial cosmic string, or even a gravitational echo from another universe brushing against our own in the multiverse's shadow. Spotting these stars is like tracking ghosts. Their motion betrays them, but untangling their signal from the noise of galactic dynamics requires forensic-level astronomy. Some candidates emerge in the outskirts of galaxy clusters, where stars shouldn't have enough energy to escape, yet they do, all streaming in the same eerie direction. Others might be intergalactic loners far from any cluster, their high-speed trajectories pointing like arrows toward the unknown, the most unsettling possibility. Dark flow stars could be remnants of a cosmic collision we'll never witness. If our universe is a bubble among others in the multiverse, a neighboring bubble might have grazed ours long ago, leaving behind gravitational scars that still tug at everything inside. The stars caught in this flow would be refugees from that ancient encounter, their paths forever marked by a border we can't cross, a horizon we can't see beyond. They force us to confront the uncomfortable truth. The universe we observe might be a backwater, a quiet eddy in a river flowing toward something infinitely larger. And these stars, racing where nothing should be, are the only messengers brave enough to whisper of the vast unknown just out of reach. At the smallest scales imaginable, the smooth fabric of space-time dissolves into a seething chaos, a quantum foam where reality itself bubbles and fractures. This isn't poetic exaggeration. It's the bizarre prediction of quantum gravity, where particles flicker in and out of existence, and even the vacuum of space churns with virtual energy. Now imagine a star caught in this primordial froth, not just shining steadily like the ones we know, but blinking like a cosmic strobe light, vanishing and reappearing as space-time writhes beneath it. This is the quantum foam star, a celestial will-o', the wisp that dances on the edge of reality. At the Planck scale, a distance so small it makes an atom look like a galaxy. Space-time isn't smooth. It's a turbulent sea of tiny wormholes, black holes, and fluctuations where energy borrows existence for fleeting moments before vanishing again. Under normal circumstances, these quantum jitters average out, leaving the universe looking calm and predictable at larger scales. But what if a star's immense gravity could amplify these fluctuations, locking itself into a precarious tango with the foam? The result would be a star that doesn't just burn. It stutters, its light dimming and flaring as pockets of spacetime around it collapse and reform. The physics here bends the mind. Quantum foam stars wouldn't fade slowly like dying embers. They'd blink out entirely, their mass and energy temporarily swallowed by microscopic black holes or wormholes in the foam. A moment later, they'd reappear as if the universe had hit pause and play on their existence. From our perspective, these stars would flicker unpredictably, vanishing for nanoseconds or years with no pattern. Here one moment, erase the next, then back again like ghosts refusing to stay buried. Telescopes might catalog them as variable stars or glitches, their true nature hidden in the noise of cosmic static. Why haven't we detected one? The challenges are immense. Current instruments aren't designed to catch such fleeting anomalies, and the timescales involved Planck time, a trillionth of a trillionth of a trillionth of a second, are beyond our ability to measure directly. Even if a quantum foam star flickered in our galaxy, its disappearances might blend into the background of instrument error or atmospheric interference. The best hope lies in next-generation gravitational wave detectors, which could sense the ripples from space-time itself shuddering around these stars, or quantum-enhanced telescopes capable of parsing the universe at previously impossible resolutions. Some theorists speculate that quantum foam stars might not be rare, just invisible by default. If the early universe was denser and more turbulent, entire generations of these stars could have formed, their flickering lives too brief to leave lasting marks on the cosmos. Others suggest they might cluster near supermassive black holes, where space-time curvature is extreme enough to tease the foam into macroscopic weirdness. There's even a haunting possibility that our own sun or any star could experience quantum foam effects under the right conditions, vanishing without warning only to reappear unchanged as if nothing had happened. The implications shake the foundations of astrophysics. Quantum foam stars would prove that space-time isn't just a stage for celestial objects, it's an active participant, capable of rewriting the rules of existence moment by moment. They blur the line between star and quantum fluctuation, between object and illusion, reminding us that the universe's deepest truths might not lie in what we can see, but in the fleeting gaps between one observation and the next. In a cosmos where even nothingness boils with hidden energy, the most elusive stars might not be hiding in darkness, they might be slipping through the cracks in reality itself. What if the stars we see aren't really there, not as three-dimensional objects, but as cosmic projections like holograms painted onto the fabric of the universe? This isn't just wild speculation, it's a radical idea rooted in the holographic principle, a theory that suggests all the information in our 3D reality might be encoded on a distant 2D surface. In this mind-bending framework, some stars could be illusions, not physical objects burning in space, but flickering images woven from deeper, hidden layers of reality. The holographic principle emerges from black hole physics, where scientists realized the information swallowed by a black hole isn't lost but smeared across its event horizon like data on a celestial hard drive. Extend this logic to the entire cosmos, and you get a universe where every star, planet, and galaxy might be a projection from some vast, unseen boundary. Imagine a holographic star. Its light, heat, and gravity would feel real to us, but its true source could lie billions of light years away, encoded in bits of quantum information we'll never directly observe. How would such a star behave? Unlike ordinary stars bound by nuclear physics, holographic stars might flicker in ways that defy conventional models. Their light could carry subtle anomalies, patterns, or delays that betray their projected nature. Some might even glitch, momentarily distorting or doubling as the cosmic projector, the hidden 2D surface, adjusts its code. Astronomers searching for these oddities would face a paradox. The stars they're studying wouldn't technically exist where they appear to be. Their true location, a flat, distant membrane where the universe stores its deepest secrets, the unsettling part, we might have already spotted candidates. Certain stars exhibit bizarre luminosity shifts that don't match known variable star types. Others appear to warp spacetime in ways that don't align with their visible mass. Could these be holographic artifacts, their true mass and energy stored elsewhere, leaking into our reality as imperfect reconstructions? The most compelling evidence might come from gravitational wave observatories. If two holographic stars collided, the ripples in spacetime might carry fingerprints of their true, encoded origins, subtle asymmetries or echoes that reveal their illusory nature. Yet the biggest challenge is philosophical. If holographic stars exist, they force us to question what real even means in cosmology. Are we, like those stars, just projections? Is the night sky a screen displaying a cosmic film where the actors are shadows of something far stranger? The holographic principle doesn't just hide stars from view, it suggests the universe itself might be the ultimate magic trick, with celestial objects as its most dazzling sleight of hand. And if that's true, the most profound question isn't where are the hidden stars, but what else are we missing when we mistake the projection for the stage? The universe loves accidents, fleeting moments where chaos conspires to create something impossible. Among its rarest flukes could be the Boltzmann star, a celestial hiccup born not from collapsing gas or dying giants, but from pure random chance. Picture this: somewhere in the void, quantum particles jittering in the vacuum suddenly align just right, their energy briefly condensing into the structure of a star. Not for millennia, not for seconds, for a single Planck time instant shorter than a thought. Slimmer than a razor's edge, a fully formed sun flickers into existence, then vanishes as if it never was. This isn't just improbable, it's statistically absurd. The odds of random fluctuations assembling even a single atom into the exact configuration of a star are so infinitesimal they make winning every lottery in history look like a safe bet. Yet in an infinite universe with infinite time, the impossible becomes inevitable. The Boltzmann star, named after physicist Ludwig Boltzmann, who first pondered the idea of order emerging from randomness, is a cosmic mirage, a glitch in the fabric of reality where thermodynamics takes a coffee break and lets entropy run backward. What would such a star look like? Nothing, because you'd never see it. Its entire lifespan would be shorter than the time it takes light to cross its own diameter. It wouldn't ignite fusion, wouldn't radiate heat. It would simply be, then not be, a phantom so ephemeral even the vacuum might not notice. The only way to detect it would be to catch the universe mid-glitch, perhaps through some bizarre ripple in the quantum foam where the star's gravitational field briefly flexed spacetime before dissolving. The irony cuts deep. A Boltzmann star isn't a product of astrophysics but of statistics gone wild. It's the universe trolling itself, proving that given enough time and space, anything can happen, including things that absolutely shouldn't. Some theories even suggest these momentary stars might be more likely than stable ones in the far, far future, when the cosmos is cold and stretched so thin that random fluctuations become the only source of structure. And here's the kicker: if Boltzmann stars can form, then statistically, you've probably already been one. In an infinite multiverse, every possible configuration of particles must repeat infinitely, including the arrangement of atoms that makes you, briefly coalescing in the void before scattering back into chaos. The Boltzmann star isn't just a curiosity, it's a hall of mirrors reflecting our own improbable existence, asking whether we're any more permanent than a star that shines for less than a blink. So the next time you gaze at the night sky, remember, the darkness between the stars might not be empty. It could be littered with the ghosts of universes that almost were, flickering in and out of existence too fast for even time to remember. Before the first galaxies, before even the faintest glow of starlight pierced the cosmic dark, there may have been stars that burned bright and vanished without a trace, celestial phantoms whose light will never reach us, lost in the expanding fog of the early universe. These weren't just any stars, they were the universe's first experiments in illumination, blazing to life in a time so ancient, the cosmos hadn't yet cooled enough to form atoms as we know them. Meet the population Roman 3 stars, theoretical giants born from the pure hydrogen and helium soup of the primordial universe. With no heavy elements to help them shed heat, these stars could have grown to staggering sizes, hundreds of times more massive than our Sun, burning at temperatures so extreme they'd make modern stars look like candle flames. Their lives were brief and violent, ending in cataclysmic explosions that seeded the cosmos with the first heavy elements, the building blocks for everything that followed. But here's the haunting part: their light is forever out of reach. The universe was smaller then, but expanding rapidly. By the time these stars ignited, the space between them and our future cosmic neighborhood was stretching faster than their light could traverse it. Their photons, desperately racing toward where Earth would one day exist, found themselves caught in an unwinnable race against the expansion of spacetime itself. Like a runner on a treadmill that's accelerating faster than they can sprint, that light was stretched into oblivion, redshifted into undetectable infrared whispers, then erased entirely as the universe's growth outpaced it. Even our most powerful telescopes can't see them. The James Webb Space Telescope peers deeper into the past than any instrument before it, spotting galaxies so distant their light has traveled for over 13 billion years. But the phantom stars predate even those their era, called the cosmic dark ages, remains opaque to observation. The only hints of their existence come from indirect clues, the unexpected presence of heavy elements in the oldest galaxies, or subtle irregularities in the cosmic microwave background, the afterglow of the Big Bang. These anomalies suggest something. Perhaps entire generations of stars must have existed and died before the universe became transparent, the cruelest twist. Some of these stars might still exist today, their light trapped in an eternal chase with the expanding cosmos. If a population Roman 3 star ignited just beyond the edge of our observable universe, its light could be forever racing toward us, never quite arriving, like a letter mailed to an address that's always one step ahead. Others might have already burned out, their ashes scattered into the void, leaving no trace but the faintest echo in the chemistry of later stars. They're reminders of how much cosmic history is written in invisible ink. For every star we see, there could be countless others whose stories are locked away, their chapters folded into the fabric of spacetime itself. The phantom stars challenge us to accept that some mysteries won't be solved by looking, only by imagining, calculating, and daring to piece together the universe's lost prologue from the scattered clues it left behind. Most stars obey the familiar quartet of cosmic forces: gravity, electromagnetism, the strong nuclear force, the weak nuclear force. But what if the universe holds a fifth player in the shadows? Hidden among the constellations could be stars dancing to an entirely different rhythm, their cores pulsing with an unknown force that rewrites the rules of stellar physics. These wouldn't just be invisible by distance or dust, they'd be cloaked by the very laws of nature, their existence betrayed only by the subtle tremors they send through the fabric of reality. The hypothetical fifth force, often dubbed quintessence or dark radiation in theoretical models, wouldn't behave like the forces we know. Unlike gravity's endless reach or electromagnetism's push and pull, this force might only awaken under extreme conditions, inside the seething hearts of stars where matter is compressed beyond recognition. Picture a star where this force counteracts gravity not by pressure from fusion, but by an inherent repulsion woven into spacetime itself. The star wouldn't just burn, it would thrum, its core vibrating with energies that defy conventional detection. How would such a star hide? The fifth force could twist light in ways that render the star transparent across most wavelengths. Photons emitted from its surface might morph into exotic particles as they pass through the force's influence, leaving telescopes blind to its glow. Or perhaps the star's gravity, already warping spacetime, could be masked by the fifth force's repulsive effect, canceling out the distortions astronomers rely on to spot distant objects. The result, a celestial phantom, massive and luminous by all rights, yet slipping through every observational net we cast. There's precedent for this cosmic slide of hand. The result, a celestial phantom, massive and luminous by all rights, yet slipping through every observational net we cast. There's precedent for this cosmic sleight of hand. In particle accelerators, fleeting anomalies hint at interactions beyond the standard model, brief energy spikes or particle behaviors that vanish before they can be studied. If these irregularities trace back to a fifth force, stars bathed in its influence could exhibit equally erratic signatures, sudden flares with no solar trigger, or elements forged in patterns no known fusion process explains. Some pulsars, those ultra-dense neutron stars spinning with metronomic precision, show timing glitches that align eerily with predictions of fifth force interference. The hunt for these stars isn't just about filling gaps in physics textbooks. If they exist, they'd prove that our universe's rulebook is missing chapters, that forces beyond our comprehension sculpt the cosmos in silent, unseen ways. Future observatories, gravitational wave detectors tuned to higher sensitivities, or space telescopes capturing phantom photons might finally unveil them. Until then, these stars linger at the edge of theory and observation, taunting us with the possibility that the night sky is far stranger, far richer than the forces we've named so far. They challenge us to wonder, if a star can shine in a spectrum beyond our perception, what else have we missed in the cosmic dark? Most stars announce their presence with brilliant light, but what if the universe hid stars made of something that shuns the spotlight entirely? Picture a celestial object forged not from blazing hydrogen, but from dark matter. Those elusive particles that outweigh normal matter 5-to-1 yet refuse to interact with light. This is the WIMP star, a cosmic paradox where the very thing that makes it massive also renders it invisible. Unlike ordinary stars, which ignite when gravity squeezes hydrogen until it fuses, WIMP stars draw power from weakly interacting massive particles. These hypothetical particles among the leading candidates for dark matter don't collide like atoms, they pass through each other like ghosts. Yet if enough clustered in the early universe, their collective gravity could have sculpted dense clouds that collapsed into star-like structures. Without electromagnetic interactions, these stars wouldn't burn in the traditional sense. Instead, WIMP in their cores would occasionally annihilate upon contact, releasing faint bursts of energy, just enough to keep the star puffed up against gravity's crush, but never enough to glow. The formation process defies everything we know about stellar birth. In the primordial cosmos, where dark matter swirled in dense halos, pockets of WIMP might have cooled and condensed faster than ordinary gas. Without radiation pressure to resist collapse, these dark matter clumps could have grown to monstrous sizes. Some theorize to span 10 times wider than our solar system, while remaining eerily cold. Their surfaces wouldn't blaze with plasma but loom as perfect black spheres, detectable only by the way their gravity bends passing starlight or tugs on nearby galaxies. Why can't we see them? The answer lies in their namesake, weak interaction. WIMP ignore photons entirely, neither absorbing nor emitting light. Even if one lurked in our galactic backyard, telescopes tuned to any wavelength, X-ray, radio, infrared, would find nothing. The only hope of detection lies in indirect methods, searching for unexplained gravitational lenses where no visible object accounts for the distortion, or hunting for gamma-ray signatures from WIMP annihilations in regions that otherwise appear empty. Some astronomers speculate that certain dark galaxies, which rotate as if full of stars yet emit no light, might actually be infested with WIMP stars, their collective mass mimicking the gravity of a bustling stellar metropolis. The most haunting possibility, WIMP stars could be hiding in the most familiar places. The Milky Way's core, where dark matter is thought to pool, might host these shadowy giants, their presence masked by the glow of ordinary stars. Others might drift through galactic halos, invisible anchors around which visible matter clumps like glitter sprinkled on tar. If they exist, they'd rewrite the story of cosmic evolution, proving that the first structures in the universe weren't made of fire, but of something far stranger, particles so aloof they never learned to shine. They challenge us to rethink what it means to be a star. After all, if darkness can gather, collapse, and persist without light, then the cosmos might be filled with celestial actors we've never even thought to look for, silent, massive, and forever hidden in plain sight. What if a star didn't need fusion to burn? What if it could draw power from the vacuum of space itself, from the seething quantum foam that physicists say fills every inch of the universe, even in absolute emptiness? Enter the vacuum star, a cosmic engine sustained not by nuclear fire, but by the universe's most enigmatic fuel, vacuum energy. This hypothetical monster wouldn't blaze in the night sky. It wouldn't flicker, pulse, or dim. It would exist in perfect, eternal equilibrium, feeding off the infinite energy of nothingness. The concept bends the laws of physics as we know them. According to quantum field theory, a vacuum isn't truly empty. It's a storm of virtual particles popping in and out of existence, their fleeting presence lending the void a paradoxical energy density. Normally, this energy is imperceptibly small, so weak it only manifests in subtle effects like the Casimir force, where two metal plates in a vacuum inexplicably attract each other. But in the heart of a vacuum star, this energy wouldn't lurk in the background. It would dominate, amplified to staggering levels by some unknown mechanism, perhaps a twist in spacetime, or a rare quantum instability in a dying star's core. The result, a self-sustaining furnace where the act of collapse creates its own counterbalance. As gravity squeezes the star inward, the vacuum energy within would ramp up its repulsive force, pushing back with equal strength. No fusion required, no radiation escaping, just perfect stasis, a celestial object hovering between collapse and explosion for eternity. From the outside, it would appear frozen in time, its surface cold and dark, betraying none of the unimaginable energies churning within. Detecting one would be a physicist's nightmare. Without light or heat to emit, a vacuum star would be invisible to every telescope ever built. Its gravity might warp distant starlight, mimicking a black hole, but unlike a black hole, it wouldn't devour matter or spew X-rays from an accretion disk. The only telltale signs would be impossibly subtle, slight variations in the cosmic microwave background, or anomalies in the expansion rate of nearby space where vacuum energy might leak beyond the star's boundary. Some theorists speculate they could congregate in galactic voids, those vast, empty regions between galaxy clusters where their presence would go unnoticed for eons. The implications rewrite cosmology. If vacuum stars exist, they'd prove that vacuum energy isn't just a mathematical quirk. It's a tangible force capable of sculpting celestial bodies. They'd blur the line between star and space-time anomaly, challenging our definitions of what makes an object real. And lurking beneath the theory is a haunting question. Could our entire universe be nestled inside one? Some models of vacuum decay suggest that a single quantum fluctuation in just the right conditions could trigger a bubble of new vacuum physics, expanding at light speed and rewriting reality in its wake. A vacuum star might be the seed of such an apocalypse, or its lone survivor. They remind us that the universe's greatest power might lie not in the brilliance of stars, but in the silent, endless hum of the void itself. The cosmic web stretches across the universe like an invisible skeleton, vast threads of dark matter weaving through the void, pulling galaxies into sprawling clusters along their intersecting lines. But what if stars didn't just form within those galaxies? What if some ignited directly along the web's filaments, untethered to any galactic anchor? Imagine a star born in the deepest darkness, not nestled in a dense stellar nursery, but suspended alone on a rope of dark matter, its light so thinly spread it vanishes into the cosmic background. These hypothetical cosmic web stars would defy every rule of visibility. Unlike the packed brilliance of galactic star clusters, their structure would be diffuse, their hydrogen fuel stretched so thin across light years that fusion could barely spark. Picture a star not as a compact sphere, but as a wispy river of plasma flowing along a dark matter filament, glowing faintly across unimaginable distances. Even if it burned at temperatures rivaling our sun, its light would be diluted, smeared across so much emptiness that telescopes would mistake it for background noise. The reason for their invisibility lies in the cosmic web's design. Dark matter filaments are massive, often millions of light-years long, but their gravitational pull is too weak to condense gas into the dense knots needed for traditional star formation. Any stars that did ignite here would lack the tight, radiant cores we associate with stellar bodies. Instead, they'd resemble elongated nebulae with sporadic fusion flickering along their length, more like a string of dim fairy lights than a beacon in the dark. Even the James Webb Space Telescope, capable of spotting the universe's earliest galaxies, would struggle to isolate their faint signal from the glow of intergalactic dust. There's eerie evidence that these stars might not be purely theoretical. Astronomers have detected unexplained ultraviolet halos around distant galaxies' glows that shouldn't exist unless unseen stars are scattered far beyond galactic borders. Others have mapped faint, filamentary structures in the cosmic microwave background, regions where the universe's oldest light appears subtly warmed, as if brushed by hidden heat sources. Could these be the remnants of cosmic web stars, their energy bleeding into the void long after their deaths? The implications rewrite our understanding of star formation. If stars can exist independent of galaxies, then the universe's luminous matter might be far more widespread than we've assumed, woven into the darkness in patterns we're only beginning to trace. They'd also be cosmic nomads drifting along filaments for billions of years, their journeys dictated by the invisible architecture of dark matter. Some might even serve as waypoints for future interstellar travelers, not bright enough to guide but massive enough to bend spacetime, creating gravitational stepping stones across the intergalactic emptiness. But the most haunting possibility, these stars could be dying as we speak. Without the constant replenishment of gas found in galaxies, their fuel reserves would dwindle, leaving them to fade into cold, dark strands, ghosts of a universe that chose to light its hidden scaffolding, if only for a fleeting cosmic moment. They challenge us to reconsider where life might arise. If planets formed in their slender wakes, they'd orbit not a sun, but a river of pale fire, basking in twilight that stretches across light years. Days would have no rhythm, no rising or setting, just an eternal, diffuse glow against a starless sky. It's a reminder that the universe's creativity knows no bounds, crafting stars not just in the obvious places, but in the hidden seams of reality itself. Light travels fast, but not infinitely fast, and in a universe this vast, that simple fact creates ghosts. Imagine a star exploding in a cataclysmic supernova, its light racing outward at 300,000 kilometers per second. Now picture that light hitting a cosmic obstacle, a nebula, a dust cloud, and bouncing back toward us like an echo in a cavern. By the time those reflected photons arrive, centuries or even millennia after the original blast, the star itself is long gone. Its light echo lingers like a cosmic afterimage, a whisper from an event already lost to time. These aren't just delayed signals, they're chronological illusions. The most famous example is the supernova of 1572, observed by Tycho Brahe. Modern telescopes later caught its light echo ripples of 16th-century starlight reflecting off interstellar dust, visible only in the 21st century. But what if the delay wasn't centuries but millions of years or billions? In the voids between galaxy clusters where dust clouds stretch for megaparsecs, a star's light echo might take so long to reach us that by the time it does, the universe has expanded beyond recognition. The star's original light might have already passed Earth, its echo trailing so far behind that we mistake it for a faint, unrelated glimmer, or miss it entirely. The math gets eerie. Light from a star 50,000 light-years away, echoing off a dust cloud another 50,000 light-years beyond it, wouldn't reach us for 100,000 years. If that star died in the interim, its echo would be a posthumous broadcast, a signal from a corpse. Now scale this up. Some echoes might be trapped in cosmic voids so vast they won't return until the stars themselves are extinct, their galaxies dissolved into the cold expanse of the universe's twilight. We're left with light from objects that no longer exist, arriving at a time when no one remembers what they were. The cruelest twist, some echoes might never arrive at all. If a star's light bounces off a cloud that's moving away from us at near light speed due to cosmic expansion, the echo could be redshifted into oblivion, stretched so thin it dissolves into the cosmic microwave background. Other echoes might get swallowed by black holes or scattered into incoherence by magnetic fields, their messages scrambled beyond recovery. The universe isn't just hiding stars, it's erasing their final words mid-transmission. These echo stars challenge our perception of time and observation. When we look at the night sky, we're not just seeing objects at a distance, we're seeing them in the past. But echoes add another layer. They're the past's reflections arriving out of sequence, out of context, like letters from a war that ended before the ink dried. They force us to wonder how much of what we see is real, and how much is just the universe's delayed playback, a cosmic tape on endless loop where some tracks are too faint, too slow, or too lost to ever reach our ears. Perhaps the most profound echo isn't from a star, but from an idea that the universe's history isn't fixed in stone, but fragmented, folded, and still reaching us in pieces. Some stories arrive late, others not at all, and the darkest corners of space might be filled with light we'll never see, echoes from stars that shouted into the void and heard only silence in reply. Deep in the equations of particle physics, there's a tantalizing hint that every particle we know, electrons, quarks, neutrinos, has a hidden twin. Supersymmetry, the elegant theory that could unite gravity with quantum mechanics, predicts a shadow universe of sparticles lurking just beyond our reach. If these particles exist, why couldn't they clump together, igniting stars made of matter so alien it refuses to interact with ours in any way except gravity? Supersymmetry stars wouldn't just hide in darkness, they'd be fundamentally invisible, built from selectrons, quarks, and photinos instead of ordinary electrons and photons. Imagine a celestial body where every chemical process runs in reverse. Superhydrogen fusing into superhelium, releasing energy we can't see, wrapped in atmospheres that light passes through like glass. To our telescopes, these stars would be gravitational ghosts, bending the paths of distant galaxies while emitting no light of their own. Their surfaces might ripple with supernova-like explosions, their cores pulsing with dark fusion, all silent, all unseen. The formation of such a star would rewrite cosmic history. In the early universe, where sparticles might have outnumbered ordinary matter, supersymmetry stars could have been the first to ignite, their birth predating even the legendary population Roman 3 stars. Without electromagnetic interactions, they wouldn't need dense gas clouds to coalesce. A slight overdensity of sparticles drawn together by their own weak gravity might have been enough. Over time, as the universe cooled and supersymmetry broke, most sparticles would have decayed, but what if some survived, locked in stable configurations within these stars? They could still be out there, floating between galaxies like icebergs of shadow matter. Detecting them would require rethinking astronomy itself. Traditional methods searching for light, analyzing spectra, are useless here. Instead, physicists would hunt for anomalies in gravitational lensing, patches of space where light bends too sharply for the visible mass present, or stars that wobble as if tugged by an unseen companion. Some dark matter experiments, like those searching for weakly interacting massive particles, might accidentally stumble upon hints if sparticles occasionally decay near these stars, releasing a stray photon or neutrino. But the real breakthrough could come from gravitational wave observatories. If two supersymmetry stars collided, their merger would ripple spacetime without the accompanying flash of gamma rays or kilonova, a silent crash in the cosmic dark. The implications stretch beyond curiosity. If supersymmetry stars exist, they'd be smoking gun evidence for a theory that's eluded confirmation for decades. They'd prove that nature's love of symmetry extends beyond the visible, crafting stellar-scale structures from particles we've never touched. Worse yet, they might dominate the universe's mass. Recent measurements of galaxy rotation suggest dark matter is clumpier than predicted. Could undiscovered sparkle stars account for the discrepancy? Yet the most haunting possibility isn't their invisibility, it's their potential proximity. If a supersymmetry star drifted into our solar system, we wouldn't see it coming. Only the subtle perturbations of orbits, a kink in Neptune's path, a comet deflected onto a strange trajectory, might betray its presence. By the time we noticed, its gravity could already be unraveling the delicate dance of planets. They force us to confront a humbling truth. The universe might be filled with stellar-scale objects built from rules we've yet to fully imagine. And if supersymmetry is real, the night sky isn't just hiding stars, it's hiding entire mirror kingdoms of them, burning in spectra no eye will ever see. What if some stars aren't lost in space but lost in dimensions beyond our own? String theory whispers of a cosmos far grander than the 4 dimensions we experience, with reality composed of vibrating strands called branes floating in higher dimensional space. Hidden within this labyrinth of unseen geometry could lie brane stars, celestial bodies bound not to our familiar universe but to a parallel membrane, forever separated from us by the vastness of an unreachable dimension. The concept shatters conventional astronomy. In string theory's framework, our entire universe might exist on one 3-dimensional brane, floating alongside others in a higher dimensional bulk. Stars forming on a neighboring brane wouldn't just be distant, they'd be physically unreachable, their light confined to their home membrane like shadows projected on a wall we can't touch. Even if a brane star burned brighter than a quasar, we'd never see its glow unless gravity, uniquely capable of leaking between branes, betrayed its presence through faint cosmic tremors. The detection challenge makes dark matter searches look trivial. A brane star's gravity could weakly influence our universe, subtly warping space-time in ways indistinguishable from ordinary invisible mass. Some physicists speculate that certain gravitational anomalies, galaxies rotating too fast, galaxy clusters bending light inexplicably, might hint at these hidden stellar neighbors. Others propose that colliding branes could momentarily stretch the dimensional barrier, allowing particles or energy to spill across in rare, high-energy events like unexplained gamma-ray bursts with no visible source. The possibilities spiral into the surreal. 2 branes separated by a millimeter in higher dimensions could host identical stars, twins born from the same primordial gas, evolving in perfect sync yet forever unaware of each other. A supernova on their brane might ripple ours as a gravitational whisper, recorded only as a blip in LIGO data logs. Some models even suggest brane stars could be older than ours, their membranes having cooled faster after the Big Bang, granting them a head start in stellar evolution we'll never witness directly. Yet the cruelest twist isn't their invisibility, it's their potential proximity. A brane star could theoretically hover next to our Sun in higher dimensional space, separated by less than the width of an atom in a direction we can't perceive. Its warmth might seep into our brane as dark radiation, its gravity gently nudging our planets in ways we dismiss as measurement error. They could be the universe's ultimate ghosts, neighbors forever waving from a shore we can't sail to, their existence etched only in the margins of our math. They force us to confront an unsettling truth that the cosmos might be layered like pages in a book, with stars we'll never see shining between every line. And if branes can hide stars, what else might be floating just beyond the edges of our perception? An ordinary star blazes with nuclear fire, but what if the universe holds stars that don't burn at all? Not dark stars, not ghost stars, but something far stranger. Stars that exist purely as information, their entire essence encoded in the quantum fabric of spacetime itself. These aren't objects you could touch or see. Their mathematical constellations, patterns of date, are so precise they mimic the behavior of physical stars without any of the matter. The idea springs from quantum mechanics' most radical implication that information isn't just a description of reality. It might be reality. At the smallest scales, particles behave less like tiny billiard balls and more like packets of data, their properties defined by probabilities and relationships rather than tangible substance. Extend this logic to cosmic scales, and you get the information star, a self-sustaining pattern in the quantum field, a configuration of energy and entanglement so stable it mirrors a star's gravitational pull, thermal output, even its life cycle, without a single atom involved. How could such a star form? Picture the early universe, a seething quantum foam where fluctuations in the vacuum briefly crystallized into coherent structures. Most dissolved instantly, but a rare few might have achieved a kind of cosmic metastability, their information locking in, like a flawless equation balancing itself. These structures wouldn't be held together by gravity or nuclear forces, but by the sheer elegance of their encoding, a feedback loop where the information defines the geometry, and the geometry sustains the information. From a distance, they'd warp light and bend spacetime identically to physical stars, fooling telescopes and physicists alike. The eerie part, we might have already catalogued them. Some stellar anomaly stars whose spectra defy known chemical compositions, or whose lifespans contradict evolutionary models, could be information stars in disguise. Their light would carry subtle fingerprints, photons entangled in ways no fusion process should produce, or quantum interference patterns masquerading as atmospheric absorption lines. Even their deaths would betray them. A collapsing information star wouldn't leave a neutron star or black hole. It would decohere, unraveling in a burst of corrective quantum noise, an event resembling a supernova but with none of the expected debris. Detecting one would require rethinking observation itself. Traditional astronomy relies on measuring light, heat, and gravity, all properties an information star could mimic flawlessly. The breakthrough might come from quantum telescopes, devices designed to probe not just photons but the underlying entanglement of spacetime. Such an instrument could spot the telltale glitches in stellar data, regions where the universe's code seems to execute a perfect, self-contained subroutine, independent of the physical cosmos around it. The implications rewrite our place in reality. If stars can exist as pure information, then the universe isn't just described by mathematics. It might be mathematics, a cosmic processor running equations so vivid they cast shadows. Information stars would be the ultimate cosmic illusions, proving that what we call matter is just the tip of reality's iceberg. They blur the line between physics and philosophy, asking not just how stars form, but what it means to exist at all when the substrate of reality is data in flux. Perhaps the most unsettling thought isn't that these stars are hiding, it's that we're surrounded by them, their encoded fires burning in dimensions we lack the senses to perceive. After all, if a star can be written into the universe's source code, who's to say the cosmos isn't teeming with structures we haven't learned to read? The night sky might not just be a scattering of lights, but a cosmic hard drive, its brightest files flickering in plain sight, while the darkest ones hum silently in the background, waiting for an observer with the right password. Deep in the cosmic shadows, beyond the reach of any telescope, there might exist stars that don't just fade, they unravel. These aren't victims of black holes or supernova, but of something far more sinister. Phantom energy, a hypothetical dark energy variant so destructive it could tear spacetime itself apart at the seams. Unlike ordinary dark energy, which accelerates the universe's expansion gently, phantom energy grows stronger over time, a runaway force that doesn't just push galaxies apart but could eventually shred atoms, planets, even stars from the inside out. Picture a star succumbing to this cosmic predator, As phantom energy infiltrates its core, the very fabric of space between particles begins stretching exponentially. Nuclear fusion, the star's lifeblood, falters as protons and neutrons are wrenched apart by the swelling void between them. The star doesn't explode, it disintegrates, its structure dissolving like sand in a tidal wave. What remains isn't a corpse of ash or collapsed matter, but an eerie absence, a region where spacetime's expansion has outpaced gravity's grasp, leaving behind a remnant so diffuse it emits no light, casts no shadow, and bends no starlight. A perfect cosmic vanishing act, the aftermath defies detection. Traditional stellar remnants, white dwarfs, neutron stars, black holes, leave gravitational or thermal signatures. But a phantom energy remnant would be a ghost in the truest sense. Its particles, now scattered across expanding space, would be so isolated they'd rarely interact, let alone emit detectable radiation. Even its gravity would fade into the background, indistinguishable from the universe's overall acceleration. The only hint of its existence might come from stellar demographics, galaxies with inexplicable missing stars, their expected populations mysteriously thinner than physics predicts. Phantom energy's cruelty lies in its selectivity. Theoretical models suggest it wouldn't annihilate all stars equally. Older, cooler stars in thinly populated galactic regions, already teetering on the edge of stability, would unravel first. Their younger, denser counterparts in crowded clusters might resist longer, clinging to fusion until space-time stretching overwhelms them too. Over eons, the cosmos could become a graveyard of invisible remnants, their original forms erased not by collapse but by the universe itself turning against them. The most unsettling implication, this process might already be happening. If phantom energy exists, its effects could be creeping into the cosmic periphery right now, dissolving the universe's loneliest stars while we remain oblivious. By the time we notice, by the time missing stellar populations trigger alarms, it could be too late to study the mechanism in action. Phantom energy doesn't just hide stars, it erases them so thoroughly we wouldn't know where to look. They challenge our understanding of cosmic endings. Stars aren't supposed to vanish without a trace, yet phantom energy rewrites the rules, proving that the universe's greatest threats might not come from collisions or explosions, but from the silent, insidious stretching of nothingness itself. And if these stars can be unmade so completely, what else might the universe be dissolving behind our backs? Among all these cosmic ghosts and stellar phantoms, one star stands as the ultimate embodiment of the universe's hidden depths, not because it's the strangest or the most massive, but because it forces us to confront the limits of our own perception. This isn't just a star we can't see, it's a star we can't even define, a celestial paradox that exists at the edge of what science can describe. The ultimate hidden star isn't a single object, it's the idea that the cosmos might be filled with stellar phenomena so alien, so wedded to forces we haven't discovered yet that they slip through every net we cast. Imagine a star that doesn't just defy physics as we know it, but operates by rules we haven't written, or worse, rules we've written but dismissed as impossible. It could be a fusion of dark energy and quantum fields, a structure so ephemeral it only exists when observed. Or perhaps it's a relic from a prior cosmic cycle, a survivor of a Big Bang that wasn't the first, carrying signatures of a universe we'll never know. What makes this star the ultimate enigma isn't its invisibility, but its ambiguity. Unlike black holes or neutron stars, which at least fit within the framework of known physics, this star lingers in the realm of what if. It's the cosmic equivalent of a shadow that moves when no one's watching, a glitch in the universe's code that hints at layers of reality we're not equipped to perceive. Some theorists speculate it might be detectable only through its absence, a patch of space where stars should exist based on gravity's pull but don't. Others wonder if it's already in our data, disguised as noise or dismissed as instrument error, its signal too subtle for current algorithms to untangle. The cruelest irony, this star might not even be rare. the universe could be teeming with such objects, their collective mass accounting for the dark matter we've spent decades chasing. They could orbit our sun, drift through our bodies, or lurk at the center of our galaxy, their presence as obvious and invisible as the air we breathe. And yet, until we develop new tools, new ways of seeing that go beyond light, beyond gravity, beyond the very concept of detection as we understand it, they'll remain hidden in the most frustrating way possible, not by distance or darkness, but by the sheer limits of our imagination. They force us to ask, how many stars are we missing because we don't yet know how to look? The universe isn't just hiding its secrets in the shadows, it's whispering them in a language we haven't learned to hear. And that's the greatest mystery of all. From dark stars feasting on invisible matter to phantom stars whose light will never reach us, from quark stars defying the laws of physics to time-frozen stars suspended at the edge of black holes, we've journeyed through 30 of the cosmos' most elusive wonders. Each one challenges our assumptions, proving that the universe's greatest stories aren't written in the stars we see, but in the ones we can't. These hidden stars aren't just cosmic oddities, they're living lessons in humility, reminding us that for every glittering point in the night sky, there are countless others lurking in the shadows, their existence whispered only in the margins of equations or the subtle warping of spacetime. Consider the scale of what we're missing. The stars visible to the naked eye, a mere 4,000 in an ocean of hundreds of billions in our galaxy alone, and that's just the ordinary ones. Add dark matter halos, primordial black holes, and higher dimensional phantoms, and the universe reveals itself as a hall of mirrors, where what we perceive is less than a fraction of what's real. The Hubble Deep Field image taught us that even a patch of sky the size of a grain of sand holds thousands of galaxies. Now imagine how much more hides in the darkness between those pixels, in wavelengths we can't detect, in dimensions we can't access. Yet this isn't a cause for frustration, it's an invitation. Every unseen star is a puzzle waiting to be solved, a door to new physics, a reminder that wonder doesn't come from having all the answers, but from the questions we've yet to ask. So the next time you step outside and gaze up at the night sky, let your eyes linger in the gaps between the stars. That's where the real magic lies, not in the light, but in the unknown. Which of these hidden stars captured your imagination the most? Was it the quark star, where matter dissolves into its strangest form, the dark flow star racing towards something beyond the edge of reality? Or the Boltzmann star, a fleeting mirage of probability? Share your thoughts below, and remember, the universe's greatest secrets aren't just in distant galaxies. They're woven into the fabric of the sky above you, waiting for the day science, technology, and human curiosity finally pull them into the light. Until then, keep looking up. The cosmos has only just begun to reveal